controlled reactions. Part of the Many Proteins Are Enzymes topic. So, the AQA specification references required practical 1, investigation into the effect of a named variable on the rate of an enzyme-controlled reaction. Students could identify the variables that must be controlled, could calculate the uncertainty, could select an appropriate format for the graphical representation of the results of their investigation into rates of reaction, use a tangent to find the initial rate of an enzyme-controlled reaction. Measuring the rate of an enzyme-controlled reaction. So there's two ways of measuring the rate of an enzyme-controlled reaction. You can measure how fast the product of the reaction appears and use this to compare the rate of reaction under different conditions. So as an example of this, hydrogen peroxide and catalase. So catalase catalyzes the breakdown of hydrogen peroxide into water and oxygen. And you can measure the volume of oxygen produced and measure the rate of production. In this experiment, you work out the rate of reaction at different temperatures, and the oxygen release displaces the water from the measuring cylinder. Or if you wanted to be more accurate, you could use a gas syringe to collect it instead. So the method would be set up boiling tubes with the same volume and concentration of hydrogen peroxide, add equal volumes of buffer solution to keep the pH constant, set up the rest of the apparatus as shown. Put the boiling tubes in a water bath set to a different temperature, so 10, 20, 30, 40, along with another tube containing catalase, and then you wait 5 minutes for the mixture to acclimatise. Use a pipette to add the same volume and concentration of catalase to each boiling tube, then quickly fit the bung and delivering tube. Record how much oxygen is produced in the first 60 seconds of the reaction. Use a stopwatch to measure the time. Repeat the experiments at each temperature 3 times and use the result to find the mean volume of oxygen produced. Calculate the mean rate of reaction at each temperature by dividing the volume of oxygen produced by the time taken, which would be 60 seconds, and then the units will be centimetres cubed per second. Or you could measure how fast the substrate is broken down and use this to compare the rate of reaction under different conditions. So as an example, you could use the amylase starch maltose reaction. The enzyme amylase catalyzes the breakdown of starch into maltose, and you can test for the presence of starch in solution using iodine. So in this experiment, you're using this to work out the rate of reaction at different concentrations of enzyme. So put a drop of iodine into each well on a spotting tile, mix together a known concentration and volume of amylase and starch in a test tube. Use a dropping pipette to put a drop of this mixture into one of the wells containing the iodine solution at regular intervals, e.g. every 10 seconds. Observe the resulting colour, and the iodine solution goes dark blue-black when starch is present, but it remains brown when there's no starch. So you can find the rate by recording how long it takes for the iodine solution to stay brown when the starch or amylase mixture is added, and then you can repeat the experiment using different concentrations of amylase. And you could repeat it 3 times at each amylase concentration and use it to find the mean time taken. So for the amylase starch maltose reaction, the variables, the experiment shows you how you can investigate the effect of temperature and enzyme concentration on the rate of enzyme controlled reactions. And you can also alter these experiments to investigate the effects of different variables such as pH by adding a buffer solution with a different pH, or substrate concentration, and you could use serial dilutions to make different concentrations. But you need to make sure that you're only changing one variable, one independent variable. Everything else should stay the same. So estimating the initial rate of reaction. So you can use a tangent to approximate the initial rate of reaction from a graph. So the initial rate is a rate of reaction right at the start of the reaction. To work out the initial rate of reaction, carry out the following steps. Draw a tangent to the curve at t equals 0 using a ruler. Do this by positioning the ruler so it's an equal distance from the curve at both sides of where it's touching it. So here you'll have to estimate where the curve would continue if it carried on below 0. Then draw a line along the ruler. And then you calculate the gradient of the tangent. So the equation for the gradient of a straight line is change in y over change in x. When you're working out a rate, the variable on the x-axis should always be time. And then finally, you need to work out the units of rate. This unit will vary depending on what was measured. To work out the units of rate from the graph, the units of the y-axis divided by the units of the x-axis. So estimating the initial rate of reaction, the graph below shows the volume of products released by an enzyme-controlled reaction at 37. So remember, if it's the initial rate, you start it at 0, and then you draw a tangent to the curve at 0. And then you would calculate it by changing y divided by changing x. So it would be 50 divided by 18. And centimetres cubed are the unit here, and seconds is here, so it's centimetres cubed per second. So it would be 2.8 centimetres cubed per second. So rate is a measure of how much something changes over time. So calculating a rate can be useful when analysing your data. You might want to find the rate of reaction. You can find the rate from a graph that shows a variable changing over time by finding the gradient, like how steep it is. So rate is a measure of how much something is changing over time. So calculating a rate can be useful to analyse your data, find the rate of reaction and how much a variable is changing over time. So for a linear graph, you can calculate the rate by finding the gradient of a line using the equation changing y over changing x. The equation of a straight line can always be written in the form of y equals mx plus c, where m is the gradient and y is the intercept. To find the rate at which oxygen is produced in the graph on the right, pick 2 points on the line that are easy to read and a good distance apart. So these ones here are quite easy to read. The bigger the triangle that you can make, the better. And then you just do change in y over change in x. So this one would be 15, 67, 18 minus 6. And then this one would be 6 minus 2. Okay, so for a non-linear graph, you can find the rate by drawing a tangent. The tangent is a straight line that touches a single point on the curve. To find the rate of reaction when the time is 30 seconds, it's got to touch the curve at 30 seconds. And then angle the ruler so there's equal space between the ruler and the curve on either side of the point. And then you draw a line along the ruler to make a tangent. Extend the line and then draw a triangle to find the change in y over change in x. So for here, it's 23 minus 12, and this one would be 50 minus 12, and then you do the change in y over the change in x, so you get 0.29 centimetres cubed per second.